Quantum computers are revolutionary machines that utilize some of the most bizarre yet potentially world-changing principles of quantum mechanics to perform computations. At the scale of atoms and subatomic particles, the weird rules of quantum mechanics dictate that particles such as photons and electrons are able to exist in a state of superposition, meaning they can represent multiple possible states simultaneously. They can also become entangled, causing the quantum state of one particle to become intrinsically linked to another, even when separated by vast distances. It is these strange properties of superposition and entanglement that quantum computers are designed to leverage in order to carry out certain types of calculations exponentially faster than any classical computer. While traditional computers use classical binary bits that must be strictly in one state or the other, either 0 or 1, quantum computers employ qubits or quantum bits. Qubits harness their ability to be placed into quantum superposition, representing a 0 and 1 at the same time, allowing quantum computers to perform parallel processing on immense data sets. Even just a few dozen qubits theoretically could be exponentially more powerful than the fastest supercomputers ever built for problems related to factorization, simulation, machine learning, and optimization. There are a few different architectures being developed for building practical quantum computers capable of tackling useful real-world problems. Superconducting qubits consist of tiny superconducting circuits patterned onto chips that act as artificial atoms, with two distinct quantum states that can represent 0 and 1. Trapped ion qubits use individual charged ions like calcium or magnesium that are levitated in place by electric fields and lasers, with quantum states encoded in their internal structure. Quantum dot qubits form with electrons trapped on semiconductor chips, where the electron's properties like spin or orbital state carry information. Photonic qubits leverage single photons and linear optics to create entanglement between particles of light. Each approach has its own strengths and weaknesses that engineers work to optimize, balancing coherence time, scalability, error rates, and other factors to reach the elusive goal of quantum supremacy. To truly harness the potential of quantum computing, the hurdle of building quantum computers with enough robust qubits operating coherently remains incredibly challenging. Individually, quantum systems are extraordinarily fragile and delicate, prone to disturbing interference from ambient vibrations, electromagnetic radiation, or even interactions with their surrounding environment. Exposing the quantum states needed for computation directly causes them to decohere or lose their superposition rapidly. For frame of reference, the typical coherence times for leading quantum hardware today may range from microseconds to milliseconds, far too short to perform anything but the most basic calculations before errors accumulate. Research teams at companies like IBM, Google, Intel, Rigetti, IonQ, and startups are aggressively developing various methods to overcome decoherence. Error correction techniques such as quantum error correcting codes operate by encoding quantum information redundantly across many physical qubits to detect and correct errors as they occur. Quantum annealing and holonomic quantum computing explore alternative computational models better suited to near-term hardware imperfections. Improved materials, chip design, and precision controls attempt to isolate qubits as much as physically possible from disruption. Microfabrication advances are continually refining superconducting and semiconductor qubit designs for denser integration. Trapped ions benefit from laser cooling and quantum logic gate improvements. Sophisticated pulse sequences precisely manipulate and entangle qubits on extremely short timescales. While still in early stages, quantum processors are gradually scaling up the number of operable qubits they can handle without error. IBM has publicly released cloud-based quantum systems with over 50 superconducting qubits. IonQ claims the highest fidelity 2-qubit gates in the industry, using dozens of trapped atomic ions held in place by electromagnetic fields under ultra-high vacuum. Honeywell commercialized the world's most powerful quantum computer to date in 2021 with a 64-qubit system. China's Tencent and Baidu also unveiled quantum processors containing more than 50 qubits each. These early devices can run basic algorithms to benchmark performance, but are not yet at the scale needed for true quantum advantage. The quantum computing industry encompasses large tech companies, as well as hundreds of smaller startups actively researching different physical implementations. Academia plays a key role in advancing fundamental science and multidisciplinary quantum sciences like materials engineering, nanofabrication, low-temperature physics, quantum information theory, and more. Public-private partnerships through government programs worldwide encourage everything from basic quantum research to applications development. An entire quantum-focused supply chain has emerged, with companies designing new materials, manufacturing qubits, developing equipment for characterization and control. Quantum applications development targets near-term algorithms to demonstrate utility, from quantum simulation of molecules and chemicals to optimization problems in logistics, machine learning, and quantum chemistry. When quantum computers eventually reach the promised quantum advantage, they may accelerate progress exponentially across every sector, from drug discovery to machine learning, chemical manufacturing to finance. Materials could be engineered with unprecedented precision, new battery and solar technologies discovered, climate and pandemic models refined with quantum speed. Encryption and blockchain technologies would require complete redesign for security against quantum threats. While there is no consensus on precise timelines, most experts agree quantum computational supremacy could be achieved within the next 5 to 10 years if current exponential qubit improvement rates hold. After that point, the pace of innovation may accelerate as quantum computers begin tackling previously infeasible problems. Quantum startups aim for on-demand access to practical quantum processors within the next decade to drive quantum applications mainstream.
Subscribe to my channel.